So we're now on page 16 and we're continuing with the experiment to prove that we need to change the distance from the pivot and our masses to balance a meter stick. So we are given our meter stick here. Okay. And it shows that the center point is 50 centimeters. It's a 1 meter stick. We have been given a position of our pivot, and the pivot is some way between the 50 centimeter mark and the end of the meter stick. So if we were to put a distance here of say 6 centimeters and we hang our mass here, okay, we want to be able to balance this ruler, because at the moment if we were to have that in the lab, the meter stick would be anti-clockwise moving this way. Okay, it'd be turning this way. So we want to be able to turn it back and balance it in a clockwise motion. So remember the principle of moments. The longer the distance away from the pivot, the greater the turning force. Okay, so we have this pivot and we know then that we need to move it out further from the pivot to get a balance. So for instance, if we were to do this in the lab, we would try it at, say this is 50, we would have it at 60 centimeters, 70 centimeters, 80 centimeters, and so on. So say for instance, we have calculated that and we get that our distance is 16 centimeters. And that is the point where the mass on this side of the clockwise movement is equal to the mass or the force or the turning point on the other side. And now we're ready with this information, we can then calculate it. So on your paper itself, you'll be given all this information and you'll be asked to calculate this. So we already know that our clockwise movement, we'll just say that our force is equal to 1 Newton, okay? So we want to do force times distance, and our force is 1, and we multiply it by our distance, which is 6. And then over here, we don't know what our force is, but we know that our distance is 16. So if we calculate this out, we get 6 is equal to 16F. And we want to get F on its own. So if we bring over our 16, we get 6 divided by 16 equals our force. This is the amount of the mass that we need to add to the slotted mass on our meter stick to balance the whole thing. And when we divide that in, we get 0.38, and the force is newtons. So if we just move it up to the top of the page here, we were given the details that the force was 1. So this little mass is equal to 1 Newton. And to balance it, we need to have, at 16 centimeters, we need to have a force of a mass of 0.38 newtons. So it's just putting it into real action, what the principle of moments is. And there's just one more thing to remember before we leave this. In most questions, you can ignore an object's weight because its weight does not have a moment if it acts at the pivot, which is usually the midpoint. So we have down here is the midpoint. Or the pivot. So here we have 2 meters and we have 1 meter, and when we have 1 meter of a distance from the pivot, it's 1000. But if we have a look here, we can see that if we double the distance, we get what would we expect here? We would half the force, okay? And in this one here, the weight doesn't come into it because our pivot is the center point. That was just, the practical was an unusual one because the pivot wasn't where the turning force was acting on. It wasn't midpoint of the ruler, okay? It wasn't at 50 centimeters. The pivot was actually starting off at an imbalance and we had to balance it. So that completes our turning forces. The next topic that we're looking at will be density. And we'll be investigating a few practicals with our density and some density problems. And that will finish the booklet off.